All right, we are in section 9.2, which is all about reflections, and especially reflections on the coordinate plane. But we're going to just talk about reflections in general. It's another type of transformation. Um, so if you recall when we talked about transformations last time, we also learned about what rigid motions are, and rigid motions basically are if you have the pre-image going to the image, if it does not change its size or shape, it's a rigid motion. So essentially, if the shape ends up being congruent, just relocated, it's a rigid motion. So we're going to talk about reflections though today, and we'll talk about whether reflections are rigid motions or not. Um, but let's start off with a couple things about reflection. So a reflection, here's a key term for you. Across the line M is called, or the line is called a line of reflection. The reflection is actually what's happening to the figure. So if a point A on the line M is on the line M, then the image of A would be itself. So right here, when you're reflecting something, if it's on the line of reflection, it does not move. It stays right there. But if you have a point not on the line, so point B over here, um, it would be the same when you reflect it. B prime, or its image, would be the same distance away from that line of reflection. And it would form a perpendicular bisector. All right? Um, we write the reflection. There's a way to reflect. There's a couple different ways to write reflection. But again, we're going to use the R, capital R, for reflection. With the sub m, because that's the line, and then in the parentheses is going to be whatever we're reflecting, which in this case we're doing is P, let's say. So this is triangle P, and and it would end up being P prime. So there's another type of, well, this is really the notation, what we just talked about. Um, but more specifically, when we're dealing with like a graph, if the line, we're using capital R again for reflection, if the line is like x equals 2. That's the line, and that's what we're going to put right there. So it's whatever line we're reflecting it over. And again, in the parentheses is the shape that we're reflecting. Okay? So notation. You got to know notation, because this is going to actually be pretty similar notation to rotations, because they both start with an R. But you'll have to, you'll see the slight difference. So let's do one example here. This one says, what is the image of point P, which is 3, 4. Let's rotate. Let's put that in here. 1, 2, 3. 1, 2, 3, 4. There's point P. Um, reflected across the line, x equals -1. So we're going to write that out. First of all, we're going to say reflection across the line x equals -1 of point P. All right, x equals -1 is right. -1 would be right here. It goes through that, and it goes up and down. So there's x equals -1. Now we want it to reflect across it. So if this is the line, it has to be the same distance, and it has to form a perpendicular bisector. So same distance away. So in this case, we're 1, 2, 3, 4 away here. So we're going to go 1, 2, 3, 4 over here. And it's already, whoa, it's already a perpendicular to that line when you start going this way because of how the coordinate plane is. So this right here would be P prime. So P prime is going to be the point -3 and 4. So you might eventually see a pattern of, if you're reflecting across a vertical line, it's just the x value that's going to change. It's going to be the opposite symbol. If you're reflecting over a horizontal line, it's the y value that's going to do the opposite symbol. But you'll just see that as we go on. It's really easy to visualize it when you draw out the graph. So let's talk about some properties of reflection. So reflections preserve distance. Like we talked about, they'd be the same distance from the line, but, um, and if you're on the line, but also AB has to be the same distance as A prime B prime, because it is going to be a congruent figure even after the reflection. So that would have to be the same. Just like AC would have to be the same as A prime C prime, and the same thing with BC and B prime C prime. Reflections also preserve angle measure. So if all the angles have to be the same there. So if we have angle A and angle A prime, those are going to be the same. I'll use a different color. C and C prime are going to have to be the same. B and B prime are going to have to be the same. All right. So preserves angle measure. And then lastly, reflections map each point of the pre-image to one and only one corresponding point on its image. So there's only one point that could be reflected, could be the reflection of a pre-image. Now the question is, would this be a rigid motion? Would the reflection be rigid? And the answer is yes, because it maintains the same size and shape. And that's what a rigid motion would be. Still a congruent figure there. Alright, so we've got lots of examples here I want to go through. Let's just do this one right now, and then I've got some other unique ones. This is with the coordinate plane. So graph the points. This is going to be a whole shape we're going to reflect. Graph the points -3, 4. 1, 2, 3, 1, 2, 3, 4. That's point A. 0, 1. 0 over, 1 up. That's point B. And, whoops. And then 4, 2. 1, 2, 3, 4. Up 2 would be right here. That's point C. Just for visualizing. We want to do a reflection across the x-axis and of triangle ABC. So the x-axis, I'm going to write the line of reflection in red. So we know this is what we have to reflect it over. So if we're reflecting it over a horizontal line, everything, really all the ordered pairs would just be, the y value would change. So if I look at it, this is what I'm going to make a hypothesis that A prime is going to be -3, -4. B prime is going to be 0 and -1, and C prime is going to be 4 and -2. That's just what I'm guessing. But let's look at the actual picture. This is 2 away from this line, so we're going to go 2 this way. So here's our C prime. 1 this way, so we're going to go 1 this way. That's our B prime. And A would be, let's see, 1, 2, 3, 4 from this line. It's going to be 1, 2, 3, 4 from there. And that would be A prime. So if we draw our shape, again, this is the same distance there. Whoops. Whoops. There we go. It looks like it just reflected over that axis. And again, my red line's a little bit off there, but if we look at the ordered pairs, this would be 4, -2, which is what I said for C prime. 0, -1 for B prime, and -3, -4 for A prime. So really, when you're doing it over the x-axis, you change the y values, make the opposite symbol. And it'd be opposite for doing it over a vertical line. All right, let's just do a few more examples with any just random reflections, and then we'll be done with this video. So example 3, it says each triangle in the diagram is a reflection of another triangle across one of the given lines. How can you use a reflection rule to describe triangle 1? So triangle 1 looks like it's reflected over the line M of triangle 3. So triangle 1, we're going to say reflection over line M of triangle 3. And that's my explanation, because if you look at it, it looks like it's the same, they're all the same distance apart on those lines. And it maintains the same shape and size. Now if I said, what about triangle 2? Well, triangle 2 would be a reflection over line K of triangle 4. Looks like it, at least. That one's a harder one to tell. But if you think about these also, there is a way to make this work somehow, I think, with rotations. And we're going to talk about rotations again in a future lesson. But if you look at them, sometimes reflections and rotations have a lot of similarities between them. But we're going to talk about that another time. So let's go to example 4. Can you use the properties of reflections to prove that triangle GHJ is equilateral? Alright, so we're going to make a proof. Alright. We're given triangle GHJ and line T I'm guessing that's an angle and a perpendicular bisector. It doesn't really tell us right there, but we know that that's the line of reflection. So that's our given, we're going to say. All right. Now, based on lines of reflection, from the properties, we know that the triangles have to preserve length and preserve distance. So if we look at this, GH is congruent to, we know that GH is congruent to GJ. And that's because, what property was this? It says preserves distance, so all the side lengths have to be the same. We also know then, let's see here. Yep, we're going to say it's a property of reflection. Now, if I'm looking at this, I'm thinking, I don't know if there is exactly enough information. Now, we need to prove that the third side is congruent as well. But all we know, we don't know exactly what this is. Um, we know they're isosceles triangles, so that's good, because these angles would be congruent. Actually, the side is congruent to itself. Um, but we don't know necessarily the lengths of HD and DJ, because if they're both half, if somehow we know that they're half of like GH or GJ, then two of them would make them congruent to those two sides. If we knew it was a 30, 60, 90 triangle, that would be a great thing as well, but we don't quite know that either. So right now I'm going to say not enough information. But if you can find a way to prove this, if you think you can, come show it to me and I'll give you a piece of candy. Because I think there might be, but right now it's not coming to me off the top of my head. So we're going to move on. I want to go through one, maybe two more examples real quick here. So draw the figure's reflection image across the line. This one's tough because some points are on opposite sides of the line. So if we look at this, I'm just going to go like this. I'm going to say that same distance will be right about here. This one is going to stay on here. This one, perpendicular line going here, go to about right here. We've got here, same distance over here, about right here. And again, I am estimating. You could totally use a straight edge or a ruler and get this pretty exact if you'd like to. But for right now, here's my shape. That's not bad. Definitely could be better though. So that's my shape. That was an estimation for me. Remember, the points just have to be the same distance from that line of reflection. And the last one, reflect ABC over the origin. Ooh, this is tough, but it's actually not bad because you're just doing the same distance. So this one would just be one down and one over. So I'm gonna go one over, one down. B prime would be right here. C prime, if I go up 1, 2, 3, 4, 5, 6, and over 1, 2, 3, 4, I'm going to do the opposite. I'm going to go over 1, 2, 3, 4, and up 6. And the neat thing about this, and this is important, is that if you would draw a line between them, it has to go through the origin. And it would. All right? So that one would work. Let me erase that last part too. And I have one more. It's got to go through the origin. So 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4. What if I go 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4? I think I did that backwards because that does not go through the origin. So I'm going to go, let's do that again. Let's go 1, 2, 3, 4, 5, 6, 7 over, and 1, 2, 3, 4 down. I think I did that right. That would definitely go right through the origin if you connected those. So I'm going to erase that last one and draw the triangle, and I think I have my triangle, my reflected triangle. So take note of these three things. Um, Reflecting over an origin, reflecting over a line, and also you can definitely prove things with these properties, but the notation was a big part too. So take a look at that. I'd like you to answer the closing questions and error analysis on your own, and then revisit the goal and see how you did. Can you find reflection images of figures? All right, that is all. We'll see you later.